Oh, and one other thing I included on this drawing, maybe hard to see where you're at, I just wanted to show a chord and a secant. They're almost the same thing. Chord just has endpoints, it doesn't continue on, and a secant is the one we consider going beyond the circle itself and continuing through. So they really are the same thing. One is with arrows, one is with endpoints. A couple more definitions, probably not as critical as the ones we had previously, but they're ones you should be familiar with. You'll see a target here, and you'll see kind of like one of those hypnotizing things. I don't know what they're called. It's not a spiral, it is a bunch of circles. And this is a bunch of circles. Think about what all of these circles have in common. Or think about what all these circles have that's exactly the same. This, of course, is hard to see on the screen, but easier to see on your paper. And you'll probably look at this and go, oh, all these circles have different sizes, but they all have the exact same center. There's a vocab word for the same center. And there's a prefix for same. You've seen it before in collinear and coplanar. The prefix co or con is the prefix for same. Co or con means same, and of course centric means center. So this means same center. These are concentric circles. At any target you see with circles that have the same center are called concentric circles. Same thing over here, you got concentric circles. And you'll have to fill in these blanks because, you know, co or con means same, and of course you can see centric as center. Second word on here is the word congruent. We use the word congruent for triangles a lot. We used it for polygons a while ago. Congruent circles, I don't have any examples up here. Congruent circles have a lot of things that are equal. You could think about 1, 2, 3, 4. I left you blanks for 4 different things you can put in there. I'm not going to fill those in for you. Think about what, if two circles are congruent, what would be equal about them? And this time you could pause and fill in. I'm not going to fill anything in for you. You could certainly say they have equal sizes, and therefore they have equal diameters. If the diameters are equal, they'd have equal radii, so you could do diameters and radii. If you think about formulas, and if their radii were equal, or if their diameters were equal, think about the two formulas you derived right before the break in Chapter 9. You could say the distance around would be equal, or the circumference would be equal. You could say the space inside would be equal. That would be the area. So there's 4 good examples. There probably are other ones you could put in there. Basically, everything's equal. They don't have to be in the same location, but they have the same amount of space, same size, same dimensions. The second little definition I want to have here, this is more of an example. You know, what type of diagram this is. You've used this in probably other classes. A Venn diagram is an example of circles with blank points of intersection. Well, there's 1, 2 points of intersection. So that's what this one is, a Venn diagram, just an example of 2 points of intersection. I want to talk about tangent circles. If you were to take these 2 circles and start to separate them and pull this one, you know, pull the one on the right to the right, pull the one on the left to the left, just a little bit to the point where they have one intersection point, they're just barely touching, that's called tangent circles. Exactly the same as when a line just barely touches in one location. The same word is used for circles as well as lines. So there's the sort of the situation I'm talking about. If you were to separate these, you'd get something like that. And there's another way you could draw this. To draw, this is called externally tangent, where they're outside of each other. If you were to flip this over and put it inside here, you'd have something called internally tangent. They only touch in one spot, so they're still tangent. There's a point of tangency, and there's a point of tangency. They only touch in one location. Again, the word tangent, in terms of relating to circles, relates to a point they have in common, the one point they have in common. All right. Another vocab term that's going to come up later, not the most important ones. The ones in the top half of the page or the first page are the most important. This is on the back. Words I think you've seen before in some word problems previously. The top one is inscribed. I can see it's sort of cut off on your screen there. Try to slide this back a tiny bit. Inscribed. You've seen the word inscribed before. Scribe, I think all of you know that the word scribe means write. And in means it's written inside. So if inscribed polygons are drawn inside of a circle, simple. So when I say inscribe a quadrilateral, I mean draw a quadrilateral inside here. Now don't just draw it randomly inside here. You want to make sure it touches the circle. And a quadrilateral, if it's inscribed, should touch it in 4 locations. Each of the corners of the quadrilateral, or each vertex of the quadrilateral, lies just on the edge of the circle. So that's an inscribed quadrilateral. Do the same thing with a triangle. Of course, the triangle will touch the circle in 3 locations. I don't care what kind of triangle you draw in there. This is going to come up a lot later on. Both of these are going to come up. These are going to be theorems later on. We're going to talk about these later on. You want to make sure you understand these, just the vocab of what's going on there. The opposite of the opposite of inscribed, some of you have seen, is circumscribed. Again, scribe means write, circum means circle. So it's a circle written about or around the circle, around the polygon. So these are just opposites. Inscribed means it's the one that's inside. Circumscribed means it's around the outside, and it relates to having a circle touch each corner of the vertex. So this would be a circumscribed circle or an inscribed triangle. A circumscribed circle or an inscribed quadrilateral. And these words can be used interchangeably. So down here, I want you to do it the other way around. I want you to draw the circle on the inside. In other words, we can use the word inscribed to describe circles. It's an adjective that describes circles. Where the circles are now inside. There's an example. The circle is now inside of the triangle. That is a triangle that's circumscribed about the circle, or a circle that's inscribed or inside of the triangle. So the vocab kind of makes sense. You just want to make sure you're clear on what you're actually drawing on your paper. I don't think I drew this for you. When you draw these, what's the new vocab word for each of these sides because of how they touch the circle? Think about your new vocab words. This one's just barely touching in one spot, barely touching in one spot, barely touching in one spot. Hopefully you realize those are tangents. And up here, when you inscribe a quadrilateral, these 4 are called chords. So you've got chords here, you've got tangents down here, because they want to just barely make contact. So a definition for inscribed relating to circles is a circle drawn inside of a polygon so that each side is, the new vocab word, is tangent to the circle. It kind of makes sense. We're now applying that vocab word, tangent. And then the exact opposite of that, in terms of wording on here, exact opposite of inscribed is circumscribed. We use the word circumscribed to describe the triangle. This triangle is circumscribed about or around. And this should say circle right here. I don't know if I changed it on your paper. That should be crossed out. A polygon is considered circumscribed about the, cross that out, circle. Hopefully I did fix that on your paper. And then I did a pentagon here. So you see each, 5 tangents are connected on there. Kind of hard to see, it's small there, but you can draw one. Make a better drawing than I have.